In this playlist, I'm going to review some experimental and theoretical works that paved the path to the discovery of quantum mechanics. The first phenomena at the top of this list is known as blackbody and blackbody radiation. However, before coming to the concept of what a blackbody and its radiation are, let me kick off by first discussing another very basic concept, and it starts from a very fundamental question, that is, how do we see objects? We see objects by means of energy known as light. This energy from an object reaches our eyes and produces the sensation of vision. However, the process by which energy reaches our eyes are of two different nature, namely reflection and emission. These are fundamentally two different physical processes. At ordinary temperature, objects are seen due to reflection of light from their surfaces. However, at higher temperature, in addition to reflection, objects are seen by the light they emit. A glowing coal, for example, emits a significant fraction of energy in the visible spectrum and hence can be seen in a darkened room. Other objects in the same room at much lower temperature do not emit an appreciable intensity in the visible part of the electromagnetic spectrum and are therefore not visible. All objects absorb and emit electromagnetic radiation whose rates depends, along with other factors, on temperature. That is, the emission rate is greater at higher temperature and the absorption rate is greater at lower temperature. At equilibrium, the two rates become equal. Otherwise, the body would spontaneously become warmer or cooler than its environment, which is against the concept of thermal equilibrium. So a good absorber of radiation is also a good emitter. At ordinary temperature, that is well below 600 degrees Celsius, the energy of emitted radiation corresponds to the electromagnetic spectrum of longer wavelengths. And at elevated temperature, the quantity of radiation increases and shifts toward the spectrum of shorter wavelength. Above 600 degrees Celsius, most of the energy of radiation lies in the visible spectrum and the object glows dull red and becomes bright red to white hot at still higher and higher temperature. Furthermore, beside the temperature, the radiation emitted by a body also depends on the nature of its material and the shape of its surface. However, if the radiation whose quality and quantity emitted by a body depends solely on its temperature, it is called thermal radiation. Now, with this background in mind, we are in position to define a black body. When the thermal radiation consists of different wavelengths hits the surface of a body, some wavelengths are absorbed and the rest are reflected. A body that completely absorbs the thermal radiation of all wavelengths hitting its surface is called a black body. So for thermal radiation, a black body works as an optimal trap. On the other hand, if a black body is heated, then the thermal radiation emitted by such a body is called black body radiation. But keep in mind, no ideal black body naturally exists. However, an approximate one can artificially be constructed as the one shown in the figure. It consists of a hollow body with a narrow opening leading to its interior. The inner surface of the cavity is coated with a lamp black. When irradiation of any wavelength once enters through the narrow opening, it may go through a number of reflections and is ultimately totally absorbed with negligible chance to leave the cavity back through the opening. Now, if the temperature of this cavity is raised, it emits radiation of all wavelengths through the opening and bears the characteristic of what we call black body radiation. Now let us get acquainted with the terminology regarding the black body radiation. And the first thing I'm introducing is the isothermal enclosure, a cavity whose walls and contents are all at the same temperature is called an isothermal enclosure. In an isothermal enclosure, the stream of radiation in any given direction must be the same as in any other direction. It must be the same at every point inside the enclosure. Otherwise, there will be regions of high and low energies or temperature that will enable us to run a heat engine within the same isothermal enclosure, which is a violation of the second law of thermodynamics. The next thing is called total emissive power or radiant intensity. It is defined as the total radiant energy emitted per unit time per unit area of the surface of the radiating body. Since energy per unit time is power, therefore it may be defined as the total radiant power per unit area. The total emissive power is usually denoted by capital I, and it increases rapidly with increasing temperature. As the energy of the spectrum of a cavity radiator is distributed in various wavelengths in a regular manner, so it is needed to know the amount of energy radiated in different wavelengths. This is done by introducing another quantity which is called spectral radiancy. The spectral radiancy is defined as the radiant power emitted in the spectral range from lambda to lambda plus d lambda per unit area. If capital R represents the emissive power per unit area, then R sub lambda times d lambda represents the emissive power in the spectral range spanning from lambda to lambda plus d lambda. From this, the total emissive power can be found by integrating the spectral radiancy over the complete range of wavelength. That is, the total emissive power I as a function of t is obtained integral from 0 to infinity r sub lambda times d lambda. Keep in mind, this is a very important relation for understanding the theory of black body radiation. There is another important quantity called emissivity. The emissivity of surface is defined as the ratio of its total emissive power to the total emissive power of a black body at the same temperature. It is usually denoted by epsilon and is obviously mathematically expressed as epsilon equal I divided by I naught, where I is the emissive power of that particular surface and I naught is the total emissive power of a black body at the same temperature. It is obvious from this equation that emissivity is purely a number with no dimension and is only equal to 1 for a black body. So from this we can redefine black body as the body with emissivity equals 1. In the next video in this playlist, I'll be reviewing the laws of black body radiation. So don't miss, be tuned, stay with me.